All right, welcome to a new lesson. Today we're learning about ions. Again, today we're learning about ions. So what's so exciting about ions? Let's get started and we'll see. Before we even get into the discussion of what an ion is, I want you guys to look at this color wheel and these small dots here. Okay? The color wheel simply tells us which colors are opposites of one another. Blue and orange are opposite, so they cancel each other out. Purple and yellow are opposite, so they cancel each other out. And then red and green are also opposite, so they cancel each other out. And what cancel each other out in this instance is if I were to draw something that was red and then I just didn't want that to be seen anymore, I would shade over it with green. So that is what the color wheel shows us. We're using these dots to kind of represent the same thing. Red and green are opposites. Because they're opposite to each other on the color wheel, they cancel each other out. Therefore, the net color would be neutral because in this instance, there are an equal number of red and green circles. So I have 1, 2, 3, 4, 5 red circles and 1, 2, 3, 4, 5 green circles. So they're perfectly neutral because I have the same amount of each circle, each color. So what happens then, do you think, if one color had more or less than the other? That's what we're going to discuss now. All right, so in this instance, sorry about how this looks, it's kind of ugly. So in this instance, I have 1, 2, 3, 4 red and 1, 2, 3, 4 green. What happens if I take away one of the red dots? You won't be able to see it here, but if I were to take away one of the red dots, how many red dots would I have left? Correct. I have 3 red dots left. And how many green dots would I have left? I'd still have 4. So how many more green dots do I have than red? 1, which means that the net color of these combined would be green. 1 green. Let's do it again. I have 5 reds and I have 5 greens. What happens if I take away 2 reds? How many reds am I left with? And how many green? Still a 5. And 5 minus 3 equals 2. So my net color is 2 green. Okay? Perfect. Great. Let's do it again. What is the net color of these 2 colors here? I'll give you about 30 seconds to add that up. Great. So what net color did you get? Yes, you should have gotten 3 green as the net color because you have 2 reds, but you have 5 green. So that means that your 3 extra green outweigh the 2. Let's try it again. What's the net color in this instance? Perfect. You have 7 red and you have 5 green. So that means you have 2 more red than green. So you have a net color of 2 red. So now let's make a formation. In this particular arrangement, let's say that the green dots are trapped inside and only the red circles can be added or removed. So the green dots can't move, only the red circles can be added or removed. This arrangement should look kind of familiar. We'll talk about that as we move on though. Okay, so if I take away 2 of the red dots, what is the net color? Perfect. The net color is 2 green. What if I add red dots? What does the net color become now? Uh-huh. 2 red. So what we've noticed here is that the greens cannot move. So they haven't changed, but the reds can be added to. Again, uh-huh, 2 green should be your net color because you have 5 green and you have 3 red. So what is all of that with the circles and the color wheel and the dots and the net green? What does all of that have to do with chemistry, which is the portion of physical science that we're exploring currently? Remember your subatomic particles. Electrons are negatively charged atoms. See here. Wow, sorry again. Electrons are negatively charged subatomic particles. See here. The red now becomes an electron, a negative, which is why it's red, like a stop sign, stop, a negatively charged subatomic particle. Our protons, on the other hand, are positively charged subatomic particles. See this green. And neutrons are neutrally charged, but I haven't drawn a representation of a neutron only because although atoms are composed of all 3 subatomic particles, when we're talking about ions, we are only worried about electrons and protons. Neutrons are for what? Isotopes. You got it. Okay, so since electrons and protons are oppositely charged, aka electrons have a negative charge and protons have a positive charge, they cancel each other out, just like a positive number and a negative number will cancel each other out. When the protons and the electrons cancel out evenly inside of an atom, the net charge is 0, and we'll say that that atom is neutral. So far, we've been working with neutral atoms, atoms that have the same number of electrons as they do protons. What happens when the number of electrons changes, though? So, just a quick reminder, this should look really familiar. This is what I drew previously here when we were working with the colors, and they were just green and red. It's the same thing, it just has a little bit more meaning now. Inside of an atom, protons are in the center, in the nucleus, and electrons are on the outside in energy levels or orbitals or energy shells. Only electrons, aka the red circles, can be added or taken away. That rule has not changed. So let's put the net color theory into action with electrons. So this atom has 4 protons and 4 electrons. Would anybody like to tell me what atom this is? If you said beryllium, You are correct. So beryllium is atomic number 4, which means that it has 4 protons and 4 electrons. That means that it has 4 positives and 4 negative charges. Because positive 4 plus negative 4 equals 0, they cancel out, and the atom has a charge of 0. This is a neutral atom of beryllium. What happens when I change that? Okay? So for example, here, I've taken away one of the electrons. So to find the net charge, you're simply going to add the number of positive charges and the number of negative charges. And make sure you don't change the signs. So for this, we would add positive 4 plus negative 3, and we should come out with a charge of positive 1. So let's check our understanding. Remember that to find the net charge, you're just going to add the number of positive charges and the number of negative charges. What is the net charge for this atom? Great. So what you should have gotten here was that this atom has a net charge of positive 2 because it has 2 more protons than it does neutrons. You're just going to add the number of protons, that positive 4, to the number of electrons, the negative 2, and you should get a positive 2. Excellent. Again, what is the net charge for this atom? Remember not to change the signs. You should have gotten a positive 4 plus a negative 5, which would give you a negative 1. Great. These are ions. So when you add electrons, the atom will gain a negative charge and become negative. So in this instance, we had a neutral atom of beryllium with 4 electrons and 4 protons. We added 2 more electrons, and now this whole atom is negatively charged by 2, and it has become an ion. When you remove electrons, the atom loses negative charges and becomes positive. Again, we have that neutral atom of beryllium. We lost 1 electron, so that's positive 4 plus negative 3, and that gives us a positive 1 for the charge. And this is a positive ion. Okay? So a reminder that atoms without a charge are simply called atoms. Atoms with a positive or a negative charge are called ions. The number of protons always stays the same. Only the number of electrons changes. Now, how do we tell the difference between a positive ion and a negative ion? And is there a faster way to go about this than just calling it positive ion, negative ion? There is. If an ion loses 1 or more electrons, as you can see here, sodium, which normally has 11 electrons, has lost 1 electron, so now it has 10. This is a positive ion, and we call it a cation ion. I remember this by just remembering that cat have paws, and so cations are positive. I know it's lame, but it works, trust me. Cations, positive, because cats have paws. If an ion gains one or more electrons, as we see that chlorine has done here, where it normally has 17 electrons, it now has 18 electrons, it becomes negative, and it's called an anion. I remember this by simply remembering that anti is opposite, and anions are opposite of positive. Okay? Is there a way to figure out what charge the ion will have in advance? Yes. We just need to look at the Bohr diagrams. Most atoms are going to form ions because they want to complete their outer orbit or energy level. Remember that electrons inside of this outer orbit are called valence electrons. In order to be stable, atoms need a full outer orbit or outer energy level with either 2 or 8 electrons because all atoms want to look like noble gases. As a note, previously we drew the electrons as circles, but I thought that the red X's would match the tone of this lesson better because we've been working with red as the color for electrons this lesson. So here we can see sodium with its 11 protons. That's an unstable atom. In order to become stable, this atom of sodium is going to get rid of its final electron in that third energy level. Doing this takes it down to 10 electrons with 8 on the valence shell or the full outer orbit, which means that its Bohr model now looks exactly like neon, which is directly to the right of it. Because all elements want to have electron shells or Bohr models that look like noble gases, which always have 8 electrons on the outer shell, with the exception of helium, which has 2, just as an FYI. Okay, so in this example, sodium loses its 1 valence electron to become a sodium ion. Pay attention again to the fact that the sodium ion has the same configuration as neon, a noble gas, and so it's stable. In the second example, we have fluorine. Fluorine has 9 electrons, 2 on the interior and 7 on the exterior. So fluorine will gain an electron to fill its outer orbit, and it becomes a fluorine ion, fluoride. Notice that fluorine also has the same configuration as neon, a noble gas, so it is stable. Why do you think that sodium lost an electron and fluorine gained an electron? What do you think is the reasoning behind that? Okay, I'm getting some really good answers. So let's see what we're looking at. Again, just a reminder, atoms just want to have a full outer orbit. 2 for hydrogen and helium, 8 for everybody else. To do this, they're either going to lose 1 or more electrons and become a cation and lose their outer orbit shell, or they're going to gain 1 or more electrons and fill out their outer shell while becoming an anion. So how do you know whether or not an element will lose electrons or gain electrons? It's basically just whatever is easier. Cations lose valence electrons because they typically have 3 or less valence electrons. So if it has 3 or less, it will lose all of those valence electrons and become a cation. For example, if it has 1 valence electron like sodium, it will lose one electron and lose its outer orbit because it's easier to lose one electron than it is to gain 7. Anions, on the other hand, have typically 5 or more valence electrons. So they're likely to gain enough electrons to fill out the outer orbit and become negative, so they're anions. So for an example, like we used fluoride earlier, or fluorine, I'm sorry, earlier, fluorine has 7 valence electrons. It's going to gain 1 to get 8 because it's easier to gain 1 than it is to lose 7. Simple, easy. Again, there is kind of like another trick to this. Generally speaking, elements on the left-hand side of the table, so your metals, your metalloids, and hydrogen, will lose their valence electrons to form cations or positive ions. In this image, that's everything in the grayish blue-black color. Whereas elements on the right are more likely to gain electrons to form anions and go negative, excluding the elements in group 18, which is the final group on the right, because those are noble gases and they are fully stable. There is a shortcut for this, but you need to have a periodic table to do this, and I actually recommend labeling your periodic table across the top. Okay? You're going to ignore the transition metal, which is the large group in the middle, the carbon family, which is group 14, and boron here. On top of your groups, write how many electrons they need to lose or gain in order to have a complete outer orbit, which is 8, or in the case of hydrogen, 2. So for our first column, all of these have a valence shell which has 1 electron. So in order to have a full outer orbit, they're all going to lose an electron. Our next group, which is group 2, they all have 2 outer orbit electrons or valence electrons. They're going to lose those 2 valence electrons. We're going to jump right over the transition metals and hop into group 13. They'll all lose 3 valence electrons because that's how many they have in their outer shell. We're going to jump over group 14 for now. And then we just do the reverse of what we previously done. Group 15 needs to gain 3 electrons. Remember that if it has 5 or more, it's likely to gain electrons in order to reach 8. Group 16, which has 6 valence electrons, will need to gain 2. And group 17, which has 7 valence electrons, like fluorine, will need to gain 1. The plus or minus signs can be kind of confusing, but this just lets you know that the atom, or the ion, should I say, is positive or negative. It's going to gain positivity because it's lost the electrons. It's going to gain negativity because it's gained electrons. Okay? So always remember that unlike in regular math, gaining electrons gives a negative charge. So an example of this is that beryllium is number 4. So it is here, the first element in the second group. Beryllium is going to lose 2 electrons, which is why it has a positive 2, to get rid of its outer orbit. When it does that, it'll be left with 2 electrons total, and that means that it will be beryllium plus 2, which is how we would tell the world that it's an ion. Or our transition metals, or multivalent ions, which means that they have multiple charges. This mostly involves your transition metals like copper, iron, gold, that whole block there in the middle, but it does also include tin, which is chemical symbol SN, lead, which is chemical symbol Pb, and a few others. Because our transition metal block has the capability for multiple charges across the block, you need more information for these in order to fully process them. We'll talk about this later when we talk about ionic bonding and ionic naming in Unit 3. So why does this matter? Why is this important? Who cares about ions? Okay? Ions are everywhere around you. You use ions when you eat table salt because table salt is sodium chloride, right? You use ions to keep your brain functioning. Neurons actually use sodium ions in their work to create a brain signal. Ions also help you control your pH, which is your acidity, and they allow you to move by controlling your muscle contraction. And if you're an athlete or if you just like the taste of Gatorade or Powerade, this is what they call electrolytes in your sports drinks. Ions are all around you and they're extremely relevant to your everyday life. Okay? So now we're going to go ahead and into the independent practice.